All right. Good morning, everybody. Thanks for coming. Sorry for a little bit of technical difficulty there this morning. I can't even blame it on being Monday, right? Because it's Tuesday. So we've been talking about internal combustion engines, right? So generally, we talked a little bit about some terminology, but today we're going to start going through the first of the two types of internal combustion engines we'll look at in this class. So the first thing we got to remember about these internal combustion engines is that they're really complicated, right? If we drew a PV diagram on, like on this graph here, right, we can see that it's really complicated, right? So it's not vertical lines or horizontal lines. It's this very sort of convoluted path that the process takes as we move through this cycle. At no point is the cycle adiabatic. In real life, we have a chemical reaction, a combustion reaction that's happening inside our piston cylinder assembly. Sometimes the working fluid is air, right? But sometimes it's this air fluid mixture or air fuel mixture. And then sometimes as we combust the fuel, it becomes, air that's weighted heavily towards carbon dioxide and weighted a little less heavily towards oxygen, right? Kinetic energy can be important because the piston's moving up and down. And everything's transient, so it's not steady state, right? Furthermore, sometimes the system is open because we talked about those exhaust and intake valves. Sometimes one of those valves is open, and sometimes both of those valves are closed, right? So instead of dealing with sort of a real life internal combustion engine, what we do in order to solve these problems with pen and paper is we make a bunch of assumptions. So we neglect combustion. Right? So we say instead that there's heat transfer coming into the system and going out of the system at certain points in the cycle. We always assume that the system is closed when we're talking about internal combustion engines, which means we use the closed version of the first law, right? Remember, delta E is equal to Q minus W. But after we make some assumptions, that becomes delta U is equal to Q minus W. We're going to assume that all of the processes are reversible, right? So that if there's no heat transfer, delta S is equal to 0. So the key with all of these processes that are going to use air as the working fluid is we got to look for those processes without heat transfer, those isentropic processes. We'll see how they're key to fixing the states here. We're going to assume the working fluid is an ideal gas, and sometimes we'll also assume that that the system has either a constant specific heat or a variable specific heat. And if it's constant specific heat, we'll sometimes call that a cold air standard analysis. Now, because we make all these assumptions, remember, every time we make an assumption, it's like we're stepping a little bit more towards the cartoon version of reality, right? So that means that qualitatively, we might understand that if we change a design parameter, like we talked about the compression ratio last class, then that will change how the system performs. But quantitatively, if I get that a problem gives me, this engine delivers 100 horsepower, I don't know if that number is exactly correct, right? But if I change something in the system, I'll be moving, my model will give me directionally what's going to happen inside the engine, right? So when we talk about the first law, right, at least after we make some assumptions about kinetic and potential energy here, we're going to get that delta U is equal to Q minus W. Now, the good thing is, at least for the Otto cycle we'll talk about today, we don't have to find Q and W. Remember, in the first third of the class, we would say, remember, we find work as the integral of PDV, and then we fix the states to find delta U, and then we use the first law to find Q. In an Otto cycle, we'll assume that all the processes that happen are simple processes, so that either they transfer heat or they have something to do with work, but not both, right? So how do I find work and heat, right? So at least in this particular cycle, the Otto cycle we'll talk about today, we'll assume that all the processes are either passive, that's really when we're interested in the heat transfer, or that they're adiabatic, when we're interested in the work. So really, we'll be finding, you can see from this, I got to fix all the states, right? And if I can fix all the states and I look at each individual process, I can find either the work or the heat from delta U, delta big U, right? So that's M times the change in the specific internal energy. right? So when I get to an equation like this, now I got to train myself to say, okay, what's the fluid, right? Because I can use the first law on any system, right? And I'll get, either delta U's or delta H's, depending on if it's closed or open. And then I say, okay, how do I fix the states? And the first question we have to ask is, what's the fluid, right? So in this case, for these internal combustion engines, the working fluid will be air or something like it, some kind of ideal gas. And that means for sure, no matter what we do, we can use the ideal gas law. There are two things we use the ideal gas law for, right? So first, sometimes maybe we want to find the mass in the system. So we look for some state where we have the most information. If we know PV and T, and we know what the gas is, so we can find the specific gas constant, then we could solve for the mass. But then other times we'll be moving in between states. And if we're doing that, what I prefer to do is to say that PV over T is equal to some constant, right? Because here I know that the mass is constant. And one of the assumptions we make about these cycles is that there's no chemical reaction happening. So the gas isn't changing, so the specific gas constant stays the same. And if that's true, then P1V1 over T1 is equal to P2V2 over T2, right? So that also comes from the ideal gas law. And if I use that equation, it turns out to be a little bit easier for my units. So if I can, when I'm moving between states, I like to use this version of the first law. But if I need to find mass or a specific temperature potentially, then I'll use this version of the equation. But I got to be careful with the units if I use sort of the full version or the real version of the ideal gas law. And this will help me a little bit, right? But I'm also probably going to have to deal with something, to find the temperatures, right? And the ideal gas law might not be the only tool in my toolbox, right? So we can use the ideal gas law more than once. We need to find the temperatures at every state, as we'll see. No matter whether we're doing constant specific heat or variable specific heat, we want to know the temperatures, right? The other thing here too, part of the reason that I have the temperature in purple, right, is because there's no temperature, there's no delta T in the ideal gas law, which means it can't be Celsius or Fahrenheit. It has to be in Rankine or in Kelvin. Right? So another thing that we do once we know the T, or sometimes how we find the T's, right, is we need to decide whether we're going to do variable specific heat or constant specific heat, right? And that's because in the first law, there is no temperature, right? We've got like W is equal to mass times the change in the specific internal energy, or Q is equal to mass times the change in the specific internal energy. So I need to find what the specific internal energy is. So there's two paths here, right? The first path is variable specific heat, right? Here, I need to actually find delta U. I'm going to find the individual values of the specific internal energy. And I'm going to look those up on table A22 if I'm dealing with air. Or today in the example, I think we use table A22E because we'll be using imperial units. If I'm using constant specific heat, then delta U is just CV times delta T, right? So I'm never actually going to find individual specific internal energies if I'm doing constant specific heat. The good news is it doesn't matter because the first law doesn't really ask us for individual values of U. It asks us for change in the specific internal energy. So I can model that as CV times delta T as long as I recognize that when I do that, I'm stepping, again, once more towards the cartoon, right? So it's a little bit less accurate. The other thing that's really, really important for all the cycles we'll do where air or ideal gases are the working fluid is we need to identify the places where we might have isentropic processes, right? So in internal combustion engines, we're assuming every process is ideal. So if there's no heat transfer, then the process is isentropic, right? So we'll look for those. These are the ones where we're either putting work into the system or we're getting work out. So if it's variable specific heat, then for internal combustion engines, what we do is we look for volume ratios, right? So we'll use this thing called VR, the reduced volume on table A22. I'll show you a little bit how to use that on the next slide. And this ratio of reduced volumes is going to be also equal to the ratio of volumes. So if you know the volume ratio, like the compression ratio, then you also know this ratio of the reduced volumes. If you're doing constant specific heat, then if we have an isentropic process, we're looking for an equation that has K up in the exponent, right? So here, if we have K in the exponent, we want an equation that has temperatures and volumes. Because typically in closed system processes, like these internal combustion engines, we'll know volume ratios, right? Whereas in open system processes, we'll know pressure ratios. So then you might want the one with K in the exponent that has temperatures and pressures. But here, because they're closed systems, we want volume ratios and temperature ratios, right? Again, here, this is not a temperature difference, right? So these temperatures have to be an absolute temperature, Kelvin or Rankine. So now we're going to talk about, that's kind of generally what we do with internal combustion engines, but now we're specifically going to talk about Otto cycles, right? So Otto cycles consist of 4 ideal or internally reversible processes. We can sketch these things out on PV diagrams or on TS diagrams, right? So the nice thing about PV diagrams, remember on a PV diagram, we can tell something about work, right? Because work is the integral of PDV. But on a TS diagram, it's nice because we can easily find these isentropic processes, which I'm saying are, kind of the key to unlock how to solve these problems, right? So our first process is an isentropic compression, right? So we can think about our piston going up and it's compressing our working fluid, right? Isentropically, so delta S is equal to 0, right? So here my volume is getting smaller and my pressure is getting bigger. My temperature is going up, but I'm at constant specific entropy. My second process is I'm going to add heat to the system, right? So now heat is coming in, right? So I'll do a sketch of what's going on with the piston on the next few slides, right? But here, so we're assuming that the volume stays constant here. So this is constant volume heat addition, right? The nice thing about constant volume processes is here on this PV diagram, that's a vertical line. So the area under that vertical line is 0, so the work is 0, right? And then we have this expansion. This is the whole reason we run the engine, right? This is like, the sparks going off, the fuel gets ignited, it tries to expand, and it pushes that piston down. So now we're producing work. This is our power stroke, and it happens isentropically. So that, so again, delta S is 0. And then here, we now, in sort of a real engine, now we have this spent air fuel mixture. We want to get it out, right? But in this, in the way we're modeling these particular cycles is we're going to say that this happens at constant volume heat transfer. So as we go now from state 4 to 1, this is sort of how we're modeling the exhaust part of the process. We're saying that at constant volume, we're rejecting heat, right? So this is how we go around both a PV and a TS diagram. It's pretty useful to understand how to draw all of these cycle analysis diagrams for the different cycles we'll talk about. Here, again, the vertical lines on a PV diagram, that means no work. That's where the heat transfer happens. And the vertical lines on the TS diagram, that means they're isentropic. So we can use, the VR ratios, and we can use expressions with K in the exponent. So it's useful to know what these diagrams look like. Now, the other thing to notice about the Otto cycle is we have 2 important volumes here. We have the large volume, this is when the piston is at bottom dead center, and the small volume when we're at top dead center. So our compression ratio is the ratio, it's always the small volume, the big volume divided by the small volume. Compression ratios are always bigger than 1, right? So here we have volume 1 over volume 2, but that's the same thing as volume 4 over volume 3, right? Because volume 2 and 3 are the same, and volume 1 and 4 are the same. So that's another thing. It's easy to pick off what volumes to use when you know how to draw these diagrams. So just kind of a sketch of how we're modeling this. This is not how an engine actually works, right? But this is kind of how we're treating these Otto cycles, right? So here's our piston cylinder assembly. Our first process is compressing the gas. So the piston goes up, right? It's a closed system, so that means the pressure is going up too. The temperature is also going up. And now this is the part that's not real, right? So here, now it's almost like the piston just dwells there for a little bit, just hangs out, and we transfer heat in. This is not how a real engine works, but this is kind of conceptually what's going on in our model, right? And this is sort of how we're modeling the ignition of the fluid, of the fuel. And then what would happen is now the gas tries to expand, and that's our power stroke. It's pushing that piston down and producing power, right? And then the last process is heat rejection. So now this is how we're modeling the exhaust part of the process, right? So it's not how a real engine works, but this is kind of like a sketch of the 4 processes that we're modeling for this Otto cycle, right? So again, these drawings are important. Now I like to draw, right, straight blue lines for work and squiggly red lines for heat transfer. So as I move from state 1 to state 2, I'm compressing the fluid. I'm putting work into the system, right? Work in, I expect this to be negative. From state 2 to state 3, I'm adding heat, right? This is the equivalent of lighting that spark plug, right? So now heat is coming into my system. And then the whole reason I do this, right, the whole purpose of the engine, right, the equivalent of the turbine for this Otto cycle, right, is the power stroke. So as I move from state 3 to 4, I'm producing work. I'm pushing that piston down. And then I'm rejecting heat from 4 to 1. It's important to note, right, so when I'm transferring heat, my volume is constant in the Otto cycle. And when I'm doing work, then my entropy, my specific entropy is constant. So if I want to know the isentropic processes here, they're the ones where I'm doing something with work. Right? So how do I solve these problems, right? So I know I start with the first law on all of these different processes. This is the first law for closed systems, right? So even to write this equation down, we're making the assumption that the system is always closed for all of these different processes, right? It's not exactly true, but it's how we're modeling the system. Then we'll neglect kinetic and potential energy. We'll look at our 4 different processes. 2 of them are going to be adiabatic, right? So that's the compression and the power stroke, right? And 2 of them are going to be passive. That's when we're adding and rejecting heat, how we're modeling ignition and exhaust. We're also going to assume all processes are reversible. So if there's no heat transfer, then that process is isentropic. So after I make all of those assumptions, what the first law tells me is that work is equal to mass times U at the beginning minus U at the end, right? Remember for open systems, it was m dot times h in minus h out, right? So here it's a closed system process, so we lose the dot, right? So it's just mass. U at the beginning is kind of like U in, right? And U at the end is kind of like U out, right? But we're talking about U's here because this is a closed system process. So we don't have H in the first law, right? So this is the power stroke. This is where we're producing power, right? So this is from state 3 to state 4. So work out is negative, or work out is positive, sorry. Heat rejection. So here we're rejecting heat. This is the opposite, right? So this is going to be M times U at the end of the process minus U at the beginning of the process, right? Just like how for open systems, it was m dot times h out minus h in. For closed systems, it's m times U at the end minus U at the beginning, because this process goes from state 4 to state 1. So we end at state 1 and we begin at state 4. The compression, right? Here we're going from state 1 to state 2, and it's about work. So this is m times U at the beginning of the process minus U at the end of the process. We expect this one to be negative. And then the heat addition is going to be m times U at the end of the process minus U at the beginning of the process, and we expect that one to be positive. So if we're talking about an Otto cycle, these are going to be the expressions that we have, right? And the thing about the Otto cycle is that remember I was talking about, we spent a lot of time talking about Rankine cycles and all the different ways we can make them complicated and stuff. The Otto cycle, you can't really make complicated. This is just what it is. It's got all these assumptions which put us into a smaller and smaller box, right? So these are always going to be the equations for Otto cycles, right? So you have an expression for work, right, is m times u at the beginning of the process minus u at the end of the process. And an expression for heat transfer, which is m times u at the end of the process minus u at the beginning of the process. So this is great. We'd have a symbolic solution, right? So now what do? Right? We say, what's the fluid? And if it's variable specific heat, we'd look on table A22 or maybe A22E. Or if it's not air, then I think you look on table A23. But if it's constant specific heat, you take all of these delta U's and you change them into CP, or CV, times delta T. Right? So remember, CP and CV, it matters when you're talking about air, because air is an ideal gas and CP and CV are different, right? So that's different than if you're talking about a liquid, right? So delta U is CV times delta T. So you could substitute that in for all of these delta U's, and then they'd all be M times CV times some delta T. So if we wanted to talk about thermal efficiency, we can still talk about thermal efficiency even though this isn't an open system. So what happens is we just lose all the dots. So it's work out plus work in, right? The signs here are different from the first law, divided by heat in, right? So work out so all these work terms are m times u in minus u out, but the masses are the same, right? So I already factored mass out of the top and the bottom here of my fraction. So this is going to be u3 minus u4 plus u1 minus u2. So the odd numbered terms are positive and the even numbered terms are negative. In the denominator, we have u3 minus u2. Right? Now, I could, if I wanted to, I could group these. So I have u3 minus u2, right? And I could group these so that I could simplify this to 1 minus u4 minus u1 divided by u3 minus u2, right? This is just some algebra. It's okay. I just wanted to show this because, remember, we can think about the thermal efficiency as the net work divided by the heat in, but I can also think about it as the net heat divided by the heat in. So here I just want to show you that that ends up being the same thing, right? So here, this was the expression that we had. We could simplify to, if you did thermal efficiency as work in minus work out, as here there'd be absolute value signs. So work in plus work out. This is the one we just got, right? But I can do Q in plus Q out as long as I get my signs right and I get the same equation, right? Which is, I mean, that makes sense, right? It's just like, in high school physics, if you did a problem with force and with energy, you're kind of supposed to get the same answer, right? Because it's the same problem, right? The universe doesn't care how you solve the problem, right? So both of these expressions give us the same thing, right? So that gives us some confidence that we didn't mess up. Okay, so now how do we go about fixing states? So the first thing is, no matter what, it doesn't matter if we're constant or variable specific heat, we can use the ideal gas law. So I like to, when I'm moving between states, because sometimes I'll know a pressure, a volume, and a temperature at one state, and then maybe a pressure and a volume at another state. So then I can use the ideal gas law this way, right? Or it's the same thing if I multiply everything by the mass, right? So this is a pressure times a specific volume, but we usually don't know specific volumes when we're talking about these internal combustion engines. Instead, we tend to know volumes, right? So here we can say pressure times volume over temperature is constant. And the reason that's constant is because it's always a closed system, so the mass is the same. And there's no chemical reactions, so the specific gas constant also remains the same. So P1V1 over T1 is equal to MR, but P2V2 over T2 is also equal to MR. So P1V1 over T1 is equal to P2V2 over T2. So it's really important for these processes, right? Because the ideal gas law is going to be really important for us. It's going to help us fix states. But it's also really important. It's not the only tool in the toolbox, right? So it's important for us to know which of these processes are isentropic. These are the same ones where we have work that we're interested in, right? Because for these isentropic processes, delta S will equal 0. So that means if it's constant specific heat, then I can use an equation that has K in the exponent. Typically, I won't say always, because always is a dangerous word, but almost always in internal combustion engines, we'll know temperature ratios and volume ratios. Here, it doesn't matter if you put specific volume or volume in the bracket, because it's the same thing, right? We would just multiply the top and the bottom by the mass to get big volume, right? So for internal combustion engines, this is the equation that we'll use because we'll know volume ratios and not pressure ratios, typically. But if we're talking about variable specific heat, then we're going to use these expressions. So again, we probably won't know pressure ratios in internal combustion engines. Instead, we'll know volume ratios, right? So on table A22, which we haven't really talked about yet, there's two columns, VR and PR. So these are the reduced pressures and the reduced volumes, right? So I'm going to show you what these are on the table and how to use them, right? So let's say I'm dealing with an internal combustion engine, right? And I'm doing a variable specific heat analysis. And my first state is 380 degrees Rankine. So I would go to table A22, or in this case, A22E, because it's in imperial units. And now, right, I actually want the values of U. So I'll take 380 and I'll go over here and I'll read off the value of U, right? But because it's an internal combustion engine, I'm also going to read off the value of VR. So now as I go from state 1 to state 2 in this process that I'm talking about, right, there is some volume ratio, some ratio of volumes. Now let's say that that ratio of volumes is such that if I take, right, so I did this opposite way, right here. Let's go back and fix that because I don't want to get the equation wrong here for you, right? So here, this is, see how the ones are on top and the twos are on the bottom? So here, this would have been VR2 over VR1. So this has got to be V2 over V1. Right? So let's say that this is done in such a way that whatever process we're talking about, the volume ratio is such that VR2 times VR1 multiplied by V2 over V1 is equal to this, 27.17. I can only use this equation if it's an isentropic process, right? So here, that means it has to be adiabatic, right? The heat transfer has to be 0. Otherwise, if I did the second law here, I would have sigma, the entropy generation rate, to be 0, or the entropy generation to be 0, but that wouldn't make delta S 0, right? So this only works when it's work being solved for. But if this process is such, so I can use this equation because it's isentropic, and I used it to find VR2 was 27.17. So now I'd go from here and I'd go use this equation to get my new VR. Now I have a new VR. So then for this state 2, I can go back and say, okay, I knew VR. So that means now I'm on this line and I have a value for U, 179.66. And if I want it, the temperature is there as well. So this is kind of how we go about using table A22 for isentropic processes, right? So typically, maybe you'll know a temperature at one state, right, at the beginning of an isentropic process, and then you'll get a volume ratio across that isentropic process, but that volume ratio will give you the ratio of VRs, and when you know the ratio of VRs, you can find the new VR, so in this case, VR2, and then you can use VR2 to find your new value of U and your new temperature. Does that kind of make sense? Okay, good. Right, so this is our Otto cycle, right? We've got these 4 ideal processes. Because this is an ideal process, if we look, one of the things that's kind of neat here is that, you know, the area inside our PV or inside our cycle for our PV diagram is the net work. right? That kind of comes from the fact that the integral of PDV is equal to work, right? And then the area, interestingly, right, the area inside our TS diagram is equal to the net heat, right? Because the net heat is equal to the net work, and you can get the heat transfer as temperature times the integral of ds, right? So it's kind of like our work is equal to the integral of PDV, right? So the neat thing about this, right, is these two things are always equal for a cycle if it's ideal, like these Otto cycles that we talk about. So from here, we can learn something about our engines if we change something like the compression ratio, right? So here I have two different compression ratios, right? So engines that have two different compression ratios, right? So here, remember our lines that are moving more or less horizontally, right? The non-vertical lines, they're at constant volume, right? So here we see our volume is changing, right? And if we went from state 1 to state 2, we'd have a smaller change in volume than if we went from 1 to state 2 prime. So there's really two Otto cycles on top of each other here, right? From 1 to 2 to 3 to 4. And then the bigger compression ratio is 1 to 2 prime to 3 prime to 4. So what we know so this is kind of helpful, right? So we made this really simplistic model for Otto cycles, but simplistic doesn't mean not useful, right? So here we can see as we change the compression ratio, the area in our cycle gets bigger, right? So if the area on this TS diagram gets bigger, then what happens is the area inside this TS diagram is the net heat, right? So if I increase my compression ratio, I'm increasing my net heat. But if I'm increasing my net heat, I'm also increasing my net work. So this means if I have two engines and the speeds are the same, and I increase my compression ratio, then I'll get more power. But the downside is I'll have to burn more fuel, right? Because I need more heat, right? So that's basically the compression ratio sort of tells us, right? And this is kind of the engineering thing, right? Is there's a trade-off. You can have, a Toyota Corolla, or if you have enough money, you can have a Bugatti, right? And they're at different operating parameters, right? So they're, fuel economy versus power output, they're at different points in that trade-off, right? So one is more about fuel economy, that's the Corolla, and one is more about power, that's the Bugatti, right? It's like 1,000 horsepower or something ridiculous, right? Right. So as we increase we're increasing our network, right? But that means, it comes at a cost. Nothing comes for free, right? So we have to burn more fuel. So it's important to know how to find, how to do the first law analysis here, right? But we're using the closed version of the first law. And the closed version of the first law only tells us the work, right? Or the heat. But, if you open up any kind of car brochure about a particular vehicle, right, it's going to talk about the power that engine delivers, right? So how do we go from work and heat to power and heat rate, right? So we need to know something about the speed of the engine, right? So here we need to know not only the work, so the work that we calculate, the net work, will be the work per cycle. So then to go to power, which is energy per second, we need to know how many cycles happen per second of that particular engine. We can do the same thing with the heat rate. That can be the heat times the number of cycles per second. And if we know that, then we'll get energy per second, which is power, right? So how do we get cycles per second? So usually when you're driving, you might have access to a tachometer, right? Which is telling you how many rotations per minute, right? So that's the rotations of the drive shaft, right? So this is spinning, right? But in order to go from rotations per minute to cycles per second, first we have to make some kind of, we'll have to do some unit conversion here, we see, right? Because one time unit is minutes and another is seconds. But we also have to go from rotations to cycles. So we need to know something about the engine, right? And maybe last time you remember we talked about like dirt bikes and like weed whackers, right? They're going to be two-stroke engines. So two-stroke engines, you're going to get 1 cycle per rotation, right? So, but a 4-stroke engine, right, needs 2 rotations of that drive shaft to get 1 cycle in, right? Because every rotation, right, if you're going to 2 in-phase points on the circle, the piston moves up, that's 1 stroke, and then down, that's another stroke, right? But if it's a 4-stroke engine, then you got to go around twice, right? Every rotation equals 2 strokes. So to get to 4 strokes, you need 2 rotations. So for a 4-stroke engine, you have to take your rotations per minute and divide by 2 to get cycles per minute. And then you're going to have to, convert minutes to seconds, right? But in a 2-stroke engine, your rotations per minute, so 1 rotation is 2 strokes, but if you only need 2 strokes to do the whole cycle, then your 2-stroke engine does 1 cycle in 1 rotation, because every rotation still gives you 2 strokes. So the thing to remember here is if you get a 4-stroke engine, you have to divide your RPM by 2 to get cycles per minute. And then you'll, convert with time to get cycles per second. As always, these things are harder in imperial units, right? Because your work per cycle, right, will be in British thermal units or BTUs. You'll get, you still need cycles per minute. And then you got to get this conversion, right, to horsepower. Because probably if you're going to read about a car engine, it's going to tell you what the power is in horsepower and not in BTU per minute. So we still have this thing where we got to go, if it's a 4-stroke engine, we got to divide by 2 to get cycles per minute, right? And then here from cycles per minute, we can go to horsepower. So these conversion rates, you don't have to memorize. They're on the equation sheet for the course, right? So, I mean, it's also it's an open book exam, so you can make your own equation sheets, but they are on the equation sheets, right? So here again, for 4-stroke engines, you divide N by 2 to get cycles per minute, and then you can multiply by 1 minute over 60 seconds if you wanted to get rotations per second, which is more what you do in metric than in imperial. Right? And for a 2-stroke, 1 cycle is equal to 1 rotation. Right? So the higher number of strokes gets the larger number in the diameter. Or in the denominator. Sorry. Okay, so now we're going to go through pretty quickly an Otto cycle example. Right? I don't think I'll have a chance to do this both in constant and variable specific heat. So you can check out, I think, the thermal shorts and the full version of this lecture for the video to see how we get the net power for this engine in both variable and constant specific heat. I'll talk through the method for variable specific heat in the lecture here. Right? So we're trying to find, so we know some things about the engine, right? So if it was constant specific heat, then I would use CV and CP, right? And for the ideal gas law, here they're nice. They gave me the specific gas constant, or R, right? I also have a partially filled state table. So I know temperature at state 1, and I know the pressure at state 1 and state 3. I know the volume at state 4, and here they told me the compression ratio, V1 divided by V2, was 10. They also told me, because to get the power, I need to know something about the engine. So they told me that it's a 4-stroke engine and that it's running at 2000 RPM. So we know there's 4 processes here, right? And I like to do tell myself where the heat and the work is, right? And then I'm going to do the first law on all of these processes, right? So here I'm going to look at all of these processes. They're all closed. I'm going to neglect kinetic and potential energy for all of them, and they're all reversible, right? So I'm going to get delta U is equal to Q minus W for all of these processes. And then for the compression stroke, which runs from 1 to 3, or 1 to 2, and the power stroke, which runs from 3 to 4, I'm going to say those are adiabatic. And then for the heat transfer processes, that's from 2 to 3 and from 4 back to 1, I'm going to say they're passive. So I'm going to get these same expressions that I got before, right? That work is equal to M times U at the beginning minus U at the end. Now, I want to find the net work, right? Because I use the net work to then get the power. So I actually don't need anything about the heat because they didn't ask me about the thermal efficiency in this problem. So what I'm going to do is I just, so I circled my expressions for work. So first I want the net work. And then when I have the net work, then I can use the information about the engine, the speed, and the fact that it's a 4-stroke engine to get the power. Right? So first I got to find the net work. So I take the power stroke and the compression stroke works and I add them together. Right? So I'm going to get this, right? So here what I did for the net work was the sum of these two works. So M times U1 minus U2 plus M times U3 minus U4. Or I can factor out the M and get the equation that you see here. Right now, this is great, except I don't know anything on the right-hand side of the equation, right? But I got a symbolic solution, right? And that's the first part of our process is always, start with the base level equations, make assumptions, and get to the symbolic equation. And this would be our symbolic equation if they were asking for work, but they're not, right? Instead, first I can check the units, right? So my mass is going to be in pounds. I think they gave that to us on the problem. I don't think I pointed that out. And delta U, when I look it up in the textbook, is going to be in BTU per pound mass, right? Or if I was using the CV value that's in the problem, right? So this will give me work in BTUs, right? Which is great, maybe if I'm talking to another engineer, but if I'm talking to a normal person, and even most engineers, if we're talking about internal combustion engines, we probably want power in horsepower, right? So first, I'm going to just get to net power. So I want an expression that will give me power as energy per unit time. So now I take the net work that I would calculate up here, right? And then I got to multiply it by the rotational speed of the engine. But then because it's a 4-stroke engine, I know that I get 1 cycle per every 2 rotations, right? So this is like energy per cycle multiplied by rotations per minute multiplied by cycles per rotation. So the rotations would cancel out here and the energy per cycle, the cycles would cancel out here. So I'd get BTUs per minute here. But I probably want this in horsepower. So then I would take my answer that I got up here and I'd drop it down in here and I'd multiply by 1 divided by 42.4, because it's imperial. It's always nice round conversions here, right? So every horsepower is 42.4 BTUs per minute. So this is my symbolic solution. Doesn't matter if I'm using constant specific heat or variable specific heat. This is my symbolic solution. I guess the good news here is I know the rotational speed of the engine. The bad news, I don't know the net work, right? But that's okay. I got an expression for the net work. But I don't know the mass. I don't know U1 minus U2, or either U1 or U2. And I don't know U3 minus U4, or the individually U3 minus U4. So the good news is I got an equation. The bad news is I know almost nothing. So now I got to start to go through, right? And I can make a choice, right? But the first thing that I'm going to choose to look at here is the mass. Because if I try to solve for the mass, I don't need to choose yet if it's constant or variable specific heat. So if I do the mass first, that's going to be the same no matter which way I solve it. So usually for these internal combustion engine problems, if you want to find the mass, you use the ideal gas law. So we know the ideal gas law. I want the version that has mass in it. So I can't use the version that I prefer where PV over T is constant. I need PV is equal to M times R times T, right? Or I can isolate for the mass, right? Mass is equal to PV over RT. So in order to solve this, the nice thing is the problem told me R, right? I don't have to look it up in the textbook. They gave me the specific gas constant. So what I'm looking for now is a specific state, any one state where I know PV and T. Because if I know PV and T, then I can use this equation and solve for M. So there's only one state that I know the temperature at, right? So here I know the temperature and the pressure at state 1. And it looks like from the table that I don't know the volume, right? Which would be a problem because then I'd be at a dead end. But this problem sneakily tells us the volume at state 1. If we remember that the process from state 1 or state 4 to state 1, right? That's the heat rejection. That happens at constant volume. So the volume here, which we were told is volume 4, and that's true, but that's also volume 1. So now I can use that. So I can use that to just get volume 1. So here at state 1, I know the temperature, the pressure, and the volume all at state 1. But now I can also, if I wanted to on my table, fill in the other volume, right? Because that's going to be V2 and V3, and it's going to be V4 divided by 10. Right? So here I could get that, right? So now, whenever you use just the base level of the, what's this called? The ideal gas law, then you always got to worry about your units, right? Because it's probably going to be in a pain, especially if it's imperial, because your pressure is going to be in PSI, your volume is probably going to be in cubic feet, right? So you got to do some stuff, right? And then we also got to convert from foot-pounds to BTU, just because of the units that we end up getting here, right? Because R has BTU in it, right? And we're going to get basically a force times the distance, right? So that's going to give us foot-pounds. So you always got to carry your units in your calculations. But if you do that correctly, you see that in this case, we have some small mass, right? 0.0015. And that makes sense because here we have, it's gas, right? So it doesn't weigh that much, right? But we do have a value for the mass. And that's good because that was one of the unknowns inside of our equation, right? So now, I used to be that I knew nothing except N, right? But now I know N and M. So now I know two different things. And I see that if I could fix these states, if I knew U1, U2, U3, and U4, or if I was doing constant specific heat and I knew delta U1, right? So U1 minus U2, and I knew U3 minus U4, then I could sub that stuff into here, which would give me the net work, and I could put the net work into here, and then I could plug this into my calculator, and I'd have the power that I was looking for. So now we're at the point where we got to fix the states, right? So we ask ourselves, what's the fluid? Right? The fluid is an ideal gas. So we have to decide, are we going to find at constant specific heat, which sometimes is called an air standard analysis, variable specific heat, which we sometimes call an air standard analysis, or constant specific heat, which is a cold air standard analysis, right? So sometimes we use those terms interchangeably, right? So now I want to fix the states. And because we haven't really done this before, I'll do this as an air standard analysis. But again, I believe in the thermal short and in the long version from the thermal lecture series videos, I do it both ways. So we're going to start at state 1 because state 1 is nice because I know the temperature. And anytime I know the temperature, that means I can go to table A22 and I can interpolate and find the specific internal energy. But just like in the example that I saw before, right, when I was telling you about VRs and PRs, if I'm doing an internal combustion engine problem, I don't just need U from the table. When I interpolate, I also want to find VR, right? So here I'm going to interpolate to find VR as well. So now from state 1, I know temperature, pressure, specific internal energy, and VR, right? And I got U1, right? So U1 is one of the 4 things that I need to do. The bad news is now I got to go to state 2. And it doesn't really look like I know anything about state 2, except, I guess, that I know that V1 divided by V2 is equal to 10, right? So V2 is 1/10 of V1. And because of that, right? So now from state 1 to state 2, I got to remember what the process is, right? This is my isentropic compression. So this, right? Remember, the key to these ideal gas problems is where are the isentropic processes? Because that's going to help me fix the state. So because I know that this is an isentropic compression and I know the volume ratio, I also know the ratio of VRs, right? So if V2 is 10 times less than V1, then VR2 is also 10 times less than VR1, right? So now I can put a value in for VR2. And the nice thing about table A22 is once I know either the temperature or VR, then I can fix the state, right? So now, just like we did in the second leg of that first example, we're going to use table A22 to interpolate, but now we're going to use VR instead of the temperature. We're going to start at VR, use that to pick off the temperature and the specific internal energy for state 2. Now this next part might seem a little bit tricky why you need this, because we're only trying to find U, but we actually do need this. We want to find the pressure at state 2 as well, right? So here I would use this version of the ideal gas law, because if I set this up, I don't have to care about units, right? Because this is going to be P2 is equal to P1 times this ratio of volumes, as long as they're in the same units, it doesn't matter, times this ratio of temperatures, as long as they're in the same units and absolute temperatures, it doesn't matter, right? So now we're going to get a pressure for state 2. So here in state 2, we used the isentropic relationship to get VR. We used VR to then interpolate to find T and U. And then we used the ideal gas law to find P2. So now we're done with state 2 and we can move to state 3. This is why we needed the pressure at state 2. Because we don't have a temperature at state 3. And we'd like state 3, we'd like to run state 3 the same way that we ran state 1. But we don't have the temperature. So that means that we need to use the ideal gas law, right? So here, we're going to use the ideal gas law, but this time from state 2 to state 3. I cannot use the isentropic relationship from state 2 to state 3 because this is not one of those isentropic processes. This is where heat is important. This should say ideal gas law for the temperature because we're going to use this to solve for the temperature at state 3. Right, so T3 is going to be T2 times a volume ratio times a pressure ratio. And we're going to see that this is 3820. The temperature at state 3 should be the largest temperature in your system, right? Because we're compressing the gas from 1 to 2, right? That increases the temperature. And then we add heat from 2 to 3. That adds more temperature. That increases the temperature more. So state 3 should have your highest temperature. Once you have that temperature, then you can go to table A22 and for that temperature, interpolate for the specific internal energy and for the new VR. So now we're going to run state 4 just like we ran state 2. Right? So now, except now our compression ratio is flipped, right? Because now instead of compressing, right, as we go from 3 to 4, we're expanding. So the volume is getting bigger, right? So whereas last time, so we recognize that this is an isentropic process. Last time we reduced the volume by a factor of 10, right? Now we're increasing the volume by a factor of 10. So VR4 has to be 10 times as big as VR3. So this becomes 5.2. But once we have VR4, then we can use table A22 and we can find U4. If I wanted to, I can also find T4, which I may not actually need. And then I could use the ideal gas law from either 3 to 4 or from 4 to 1 to find this pressure at state 4. But I typically don't do that because I don't need it for my answer. So unless the problem explicitly asks me for what's going on at state 4, I won't do that. I probably wouldn't even find T4 if I was on a test because that's one more interpolation that I have to do, which takes more time, right? Because at this point, I have all my values of U, and that's what I was doing this analysis for, right? So now I can put all this, I can get a value for the net work. And then once I have the net work, I can put that in my equation for power. And in this case, I got that this particular engine gave me 10.5 horsepower. So I appreciate you being patient with me because I did go 5 minutes over. But I did want to get through this to kind of walk you through the process. I know we didn't do it like all the algebra, But the general process here, right, is we're probably going to know the temperature at 1 and the pressure at 1. We use that to find the mass with the volume. And then we use the temperature to find U and VR. And then we use the isentropic relationship to get VR at 2. And then we use table 822 to go VR to find our way back. And then we can use the ideal gas law to find P. So I kind of think of this as going like, at state 1, you're on the left-hand side of the column of table 822, and then you move right, or you move to your right, and then you drop down, and then you move to your left, and then you move to your right, right? So it's always the odd number ones we're typically using temperature to find VR, and the even number states where you're typically using VR to go back and find the temperature. So that's all I got for you today. Like I said, if you want to see how to do this with constant specific heat, you can look, I know for sure, in the Thermal Lecture Series playlist, and maybe in the Thermal Short, I do it both ways too. I'm not sure. All right.
Thank you, Professor.
Yeah, no problem.
All right, thank you.
Have a good one, guys.